All right, welcome back. We're now on to lecture 11, quadratic functions. And once again, exam 1 is Thursday, June 4th. Open for 48 hours and is taken online through HonorLock. All right, so let's get on to some quadratic functions. Now, suppose you want to launch a cat from a catapult. So if we want to do that, well, catapult sits so high up, it's going to launch into the air and then hit the ground sometime over here. That's how we can describe the motion of the cat, right? And this cannot be modeled by a linear function. Obviously, this is not a line. But let's still have this endeavor of trying to describe the motion of a cat if we launch it from a catapult. Well, if we really want to do that, we need to investigate some stuff on quadratic functions. So, a quadratic function in general form is f of x is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. If a is equal to 0, then we just get a line, right? That's not what we want. So, what are some examples of this? Well, let's say g of x is equal to negative 3x plus 2x minus 7. Why not? Then our a value is going to be negative 3, b is going to be 2, and c is going to be negative 7. Yeah? Well, what's the domain of quadratic functions? Domain is negative infinity to infinity. What are the uses of quadratic functions? What can they model? Well, they can model and help out with gravity, population, and area, and many more things. Okay, here are some basics about quadratic functions. So let's look at functions versus equations. So I will have this paper straightened eventually. Using quadratic functions often involves solving a quadratic equations. So if we look at this function, g of x is equal to 2x squared minus x minus 15. And we want to find the x-intercepts of g of x. Well, then what do? Well, we have to set g of x equal to 0 and solve for x. Yeah. Well, if we do that, we can factor some things out and we get 2x plus 5 times x minus 3. This is going to give us two solutions. 2x plus 5 is equal to 0, or we're going to get x minus 3 is equal to 0. Well, this side's easier. This just means x is equal to 3. This side, 2x is equal to negative 5. X is equal to negative 5 halves. Right. Luckily, we didn't have to use a quadratic formula for that, but we have to solve quadratic equations often. So let's look at graphs of quadratic functions. Next time I'm going to bring some tape and just tape the bottom page down. All right, graphs of quadratic functions. The graph of a quadratic function is called a parabola, and it has two basic shapes. We either have the one on the left or the one on the right. It's concave up or concave down. And on each of these, we have a vertex. Basically, the peak, or, well, it's the peak of the highest point or the bottom of the lowest. So we either have the peak of this concave down parabola or the bottom of the concave up parabola. Okay, every parabola has a turning point. It's called a vertex, which I've labeled as V, and they're very important in many applications. Something to note about the range is it's not all real numbers. Not all real numbers. Okay? Because it has a highest point or a lowest point, it's not going to be all real numbers. So let's look at some general descriptions. All right, use transformations of f of x equals x squared to describe the general parabola g of x. Well, let's first look at this guy. F of x is equal to x squared. That means a is equal to 1, b is equal to 0, c is equal to 0. Yeah? Now, if we look at, well, let's look at this. So this guy has 0, 0 as a vertex. If we do a horizontal shift, that'll look something like this. X minus h squared, right? We're shifting to the right h units. And a vertical shift, not plus, x minus h squared plus k. If we do a vertical shift, then that brings us over here, hk, right? So we shift it so far to the right or left, h units, and then so far up or down, k units. So in this case, well, if we look at 0, this function goes to this function. This has a new vertex, h comma k. Reflections of vertical stretches, that happens when we multiply by a times x minus h quantity squared, right? And so that's x squared. So we have a vertical shift. So a horizontal shift, then reflect the vertical stretch, reflect or have a vertical stretch, and then shift vertically. We get different transitions. Okay. We will get more into this later about transformations of functions, but this gives you a little bit of a preview of what's going on. And specifically what how a horizontal shift looks on a parabola, how a vertical stretch or a reflection looks on a parabola, or how a vertical shift looks on a parabola. Okay. So let's look at standard form. Quadratic function in its standard form is written out to be f of x equals a times x minus h squared plus k. Right? The vertex of the parabola is at the point h comma k. If you remember a ways back from circles and stuff, there was a general form or a standard form for a circle, which gave the center of the circle. This is something similar, but in this case, we're working with a parabola. The basic shapes and width are determined by the a value. So if we have a parabola that looks like this, the a value is positive. If we have a parabola that looks like that and it's going downward, then the a value is negative. So if we wanted to give an example here, g of x is equal to 9 times x plus 5 minus 10, right? That should be squared. Then our vertex is going to be, remember it's h minus k, so this would be negative 5, negative 10, and it would look like this because our a is positive. Yeah. Okay. That's standard form. Let's look at an example of this. Find the vertex and intercepts of the parabola and sketch its graph. So here we have the function b of x is equal to -4 times x plus 1 squared plus 8. All right, well, first things first, let's find the vertex. This vertex is going to be at -1, 8. All right, and so let's mark that -1, 8. And a is less than 0, so it's going to look like this. Right, and here's going to be our vertex. So we need to find another point on the graph. Well, let's find the y-intercept. That is when b of x is equal to 0. Or sorry, that's when x is equal to 0. So b of 0 is equal to -4 times 0 plus 1 squared plus 8, which is -4 plus 8, which is 4. So we get the point 0, 4. So this is this guy. So if we draw, oops, roughly, this is a sketch now. That's one arm of the parabola. Now to get the other, well, parabolas are nice because they'll have this thing, let's call it the axis of symmetry. And we'll talk a little bit about this more in this lecture in a second. But along this axis, it's reflexive. So, too many colors. So instead of actually plugging in another point, say like -3 in for x and evaluating what it should be, or -2, what you can do is, because we know that this point is on the graph, we also know that the point -2, 4 is on the graph. Because parabolas are symmetric around this axis of symmetry. They reflect well. Again, we'll get to that at near the end of this lecture. But anyway, the vertex, that gives you, okay, you find the vertex, you find another point. Y-intercept is a good place to start, and then you find another point on the other arm to finish graphing out your sketch. Okay. Let us look at another example. Find a formula for the parabola with vertex 4, 10 and y-intercept -14. So this tells us, remember, this is h, k, and y-intercept of 14. That says that we are at the point 0, -14, lies on the graph. Okay, well, what was standard form? F of x is equal to a times x minus h squared plus k. Well, we have f of x is equal to a times x minus 4 plus 10. Now we need to find out what a is. Well, we're given a point, x comma y. So let's plug those in for x comma f of x and plug that in and solve for a. So we have -14 is equal to a times 0 minus 4 plus 10. -14 is equal to a, that should be squared, sorry about that. -14 is equal to a times -4 squared plus 10. -24 is equal to a times 16. A is equal to -24 over 16, which is the same thing as -3/2. Hopefully you can see that. I'll write it on the other side. So a is equal to -3/2. And so f of x, so this guy, is equal to -3/2 x minus 4, quantity squared, plus 10. And that is your formula for a parabola with that vertex and a y-intercept. of negative 14. So that's standard form. Let's look at vertex from a general form. And as it says, vertex from a standard form is pretty easy. But what about from the general form? Remember that the general form for a parabola or quadratic is ax squared plus bx plus c. And it has a vertex point of xv comma y sub v, where x sub v is negative b over 2a, and y is f of xv, or f of negative b over 2a. Okay, so if we want to look at this example and find the vertex of the parabola given by g of x by this guy, what do we have? We have a is equal to negative 2, b is equal to 8, and c is equal to 11. So xv is equal to negative b, so it's negative 8 over 2 times negative 2. It's going to be negative 8 over negative 4, or just 2. Okay? Y sub v is going to be g of xv, which is g of 2, which is negative 2 times 2 squared plus 8 times 2 plus 11 boils down to 19. Okay. So the vertex is 2 comma 19. So from general form, it's not that bad either. It just requires a little bit more work. And knowing that your vertex is xv comma yv, which is negative b over 2a comma f of negative b over 2a, right? A few different ways to write it because we've labeled it that way. But anyway, you get the general idea. So now let's go from one form to the other. Converting between forms. So let's try from standard form to general form. So here we have f of x is equal to 2 times x minus 3 squared minus 7. We want to take this into general form. Well, that's pretty straightforward. Well, general form, remember, is ax squared plus bx plus c. And this guy, what we're going to do is we're going to FOIL stuff out. If you remember from beginning of class, well, yeah, beginning of the semester. So we have f of x is equal to 2 times x squared minus 6x plus 9 minus 7 is equal to 2x squared minus 12x plus 18. This is a 9 minus 7, 2x squared minus 12x plus 11. And there we go. That's from standard form into general form. Pretty straightforward, nice and easy. Okay. The other direction, not so much, but still not terrible. Converting between forms from general form to standard form. All right, let's take a look at g of x here, which is equal to x squared minus 12x plus 10. Well, we want to change this into the form a times x minus h squared plus k, right? And remember that h comma k that's not an over sign. H comma k, this is the same thing as negative b over 2a, and in this case, g of, not f of. Your function evaluated at negative b over 2a. Okay? So from this, our function here, from general form, a is equal to 1, b is equal to negative 12, c is equal to 10. So hk is negative b over 2a, comma, that. So h is equal to negative b over 2a, which is 12 over 2 times 1. That's going to be 6. Okay? So h is equal to 6. Now for the k. K is equal to g of negative b over 2a. Well, negative b over 2a, that's 6. So this is g of 6. And if we plug 6 into here, we get numbers. 6 squared minus 12 times 6 plus 10. And that equals something. Negative 26. Yep, did that right off the top of my head. No, I just looked it up. Okay, so we now have that k is equal to 26. So this guy is 1. The a value does not change from general form to standard form. This guy is 6, and this guy is negative 26. So our function g of x in standard form is going to be x minus 6 squared minus 26. You can put a 1 here if you want, but it's kind of useless. And so there you go. A little bit more work, but still doable. Just got to remember that your h comma k is xv comma yv. Which is negative b over 2a, comma, the function evaluated at negative b over 2a. All right, let's find another way to get a quadratic function. Quadratic function from its zeros. Standard form is a way to write the quadratic function using its vertex. Another way we can write a quadratic function is in terms of its zeros, if it has any. So if we look at this function, g of x is equal to 2x squared minus x minus 15, we can factor stuff out. This is the same thing as 2x plus 5 times x minus 3. And so as x-intercepts, well, we'll write those down in a second. So another way to write this is 2 times x plus 5 halves, right? If you factor the 2 out from this term, times x minus 3. Or one more time, 2 times x minus a minus 5 halves times x minus 3. This tells us that the x-intercepts are negative 5 halves and 3. Sure, we could have solved that out here, but factor form of quadratic function is a times x minus x1 times x minus x2, where x1, x2 are the x-intercepts. Right? Okay. So that's another way we can write stuff. Let's go basically straight to an example of this to show you what's going on. So a quadratic function f of x has x-intercepts at 5 and negative 4 and has a y-intercept of 60. Write a formula for f of x in factored form. Okay, so f of x is equal to a times x minus x1, x minus x2. All right, so this is equal to a times x minus 5. That's the first one that was listed, x plus 4. Okay, so the only thing we're missing again is this little a value, and that's where y-intercept of 60. This tells us that the point 0, 60 lies on the graph of f of x, or is a point on f of x. So we evaluate that. So 60 is equal to a times 0 minus 5, 0 plus 4. Then we get 60 is equal to a times negative 5 times 4. 60 is equal to a times 20. That's an a. Divide by 20 on both sides. And we get that a is equal to 3. So f of x is equal to 3 times x minus 5 times x plus 4. And that is our factored form of the quadratic f of x. So you can write in quadratic form, general form, standard form. Each of them has their merits, and you can swap between them at any point you want. Not at any point, at any time. Poor choice of words there. Now the axis of symmetry. So all parabolas have a line of symmetry called the axis of symmetry, right? So if we look at this guy, has an axis of symmetry here, and it goes through the vertex V. And the axis of symmetry passes through the parabola's vertex. Sort of what I just said. The equation for that vertical line is x is equal to xv. Or negative b over 2a, depending on the form you're working with, right? But x is equal to xv. So what that means is if you have a point, say here, negative xy, the point over here, xy, also lies on the graph, right? You fold this half over here, and it's the exact same. Well, that's if it's at 0. So anyway, let me actually rewrite this. x1 comma y, x2 comma y. There we go. All right. Axis of symmetry. More on that. Focal point. All parabolas have a focal point or focus above or below the vertex, and it lies on that axis of symmetry. So if you remember, general form is this for your parabola. The distance, like how far above or below your focal point is going to be, it's going to be a distance 1 over 4a from the vertex. Focal points are kind of useful. We'll get to that a bit later. But anyway, it's good to have a first starting knowledge of it now. All right. Moving on to some applications. Well, hey, we can talk about our application of launching a cat from a catapult now. So let's see. It's modeled. So if you launch a cat from a catapult, the height in feet after t seconds is modeled by the function h of t is equal to negative 16t squared plus 32t plus 16. Right. So what do we immediately know about this parabola? Well, is it opening upward? Is it opening downward? Because we have a negative 16 here, we know that it opens downward, right? So we have a vertex up here, and it has a highest point. So how high will the cat go? Well, that'll happen at the vertex, right? And then how long after launch will the cat hit the ground? Well, that's when the height is 0, right? So let's first tackle how high will the cat go. How high will the cat go? As you can see from up here, if you can see that, the parabola is facing down like this, so the highest point is going to be the vertex. So let's find the vertex. xv is equal to, again, negative b over 2a. This is going to be negative 32 over 2 times negative 16. This is equal to 1. Negatives cancel out. 2 times 16 is 32, and we get 1. So YV is equal to h of xv, which is 1. And that is going to be, plug 1 in here, we're just going to get 32. Negative 16 plus 32 plus 16 gives us that positive 32. You can't read that, so I'm going to rewrite this. YV is equal to h of 1, which equals 32. There we go. So the vertex is 1, 32. This is time t and height, h of t. So the highest, how high will the cat go? It will go as high as 32 feet. After 1 second being in the air, it will be at 32 feet, and that's the highest the cat will reach. Okay, how long after launch will it hit the ground? Well, this is when we solve for h of t equals 0, when the height equals 0, right? So 0 is equal to negative 16t squared plus 32t plus 16. Okay. This does not factor out quite nicely, so we're going to leave it for now. You can use quadratic formula on this. I would first recommend that you factor out a negative 16 first to make your life easier. Minus 2t minus 1, and that, use quadratic formula on that. But anyway, you'll be able to find out how long after launch when the cat will hit the ground. And if you really want to solve it out, I'm pretty sure it's 1 plus or minus square root of 2 if you use quadratic formula on this guy. But time can't be negative, so t is equal to 1 plus square root of 2 is going to be your answer for that, where t is in seconds, I guess. Yeah, seconds. Anyway, that's how you find out when it hits the ground. Last application here. You want to build a rectangular pen for your pet rhinoceros. You have 200 feet of fencing to use. What dimension should you make the pen in order to make it as large as possible? Well, word problems. It's nice to draw a picture. So, rectangular fence. Okay, that's a rectangle. Not a good one, but that's fine. We have a width, a length, and a length, right? The area of a rectangle is length times width. Now, we are given that we have 200 feet of fencing to use. So that means to fence in this whole rectangle, i.e. to go one length, one width, one length, one width, we have 200 feet of fence available. So that means 200 feet of fence is equal to twice the width plus twice the length, right? It's the perimeter. Now, in order to find out what dimensions we should use to make the pen as large as possible, area is in terms of length and width, 2 different variables. We need to condense that and make it into one first. So we're going to use the perimeter equation to solve for one or the other. So if we divide by 2 across the board, we get 100 is equal to width plus length. Doesn't matter which one you solve for. I'm going to solve for length. Length is equal to 100 minus W. Okay? So now, area is equal to length times width, or wait a minute, I did that backwards. It doesn't matter, I just did it backwards. So area is equal to length, which is 100 minus W, times W. Okay? We want this in terms of one variable so that we can work with it. This is 100 W minus W squared. Okay? So this is a parabola. And this is a downward facing parabola. It looks something like that, right? And it has a vertex or a highest point there. It's a parabola because of the W squared, and the coefficient out in front of the W squared, i.e. the A term, is negative, okay? So if we look at the vertex, xv, that's going to be negative b over 2a, which is going to be negative 100 over 2 times negative 1, which is going to be 50, okay? And yv is going to be, well, you plug in 50 into this guy. It's going to be 100 times 50 minus 50 squared. Calculations, and you get 2,500. So what's really important is that the xv value is 50, and you get that w is equal to 50, and your length is equal to 50, right? So remember, this function is w comma a, right? So this is, so these are going to give you points, width comma area for this parabola, and so you're maximizing the area. So by finding the vertex, so your vertex gives you xv is equal to 50, i.e. you want to use 50 for your width, and that'll give you a max area of 2,500. Well, if w is equal to 50, we come back up here and we see that L is equal to 100 minus w. 100 minus 50 gives you 50 again. So width is equal to 50 and length is equal to 50. That is the dimensions of what you should make the pen in order to make the area as large as possible, which happens to be 2,500 feet. Okay? Word problems aren't bad. They're just time consuming, and be patient with them. And that is it. That is the end of this lecture.